Okay, today we are going to continue with our very last conic, the hyperbola. So this is section 10.4. We are going to talk about how to graph a hyperbola, and we will have a quiz over all three conic graphs tomorrow. So right now, you all should have a hyperbola in front of you on a half sheet of paper. If you don't, pause the video now and make sure that everybody has one. What I would like you to do is I would like you to plot 3 points on your hyperbola, and they can be anywhere. They can be on the same branch, they can be on different branches, but what I'd like you to do is plot 3 coordinates. Okay? I then would like you to take the rulers. If you don't have a ruler, pause the video now, make sure everybody has a ruler. But what I would like you to do is measure the distance from each focus point. So there are 2 foci here. I'm going to highlight them in red. Here's one focus, here is a second focus. And what I would like you to do is take that ruler and I want you to measure the distance from your coordinate to both foci. And go ahead and label whatever that distance happens to be. Okay? Obviously mine aren't 2 and 3, but go ahead for each coordinate, measure the distances from each focus and write them down. I'm going to give you about 30 more seconds. Okay, now what I would like you to do is I would like you to take a coordinate and find the difference of your 2 measurements. For each coordinate, please do this, take the 2 measurements to the foci and subtract them. For each coordinate, take the 2 measurements and subtract them. Turn to your pod and tell them what you notice about the differences in the measurements at each coordinate. Okay. Now, since we are measuring and we are humans, there is a little bit of room for human error here. But what should happen is that the 3 different coordinates that you chose, while they had different distances to the foci, when you subtract the distances from the coordinate to each of the foci, the difference should be the same from coordinate to coordinate to coordinate. Okay? And this is the geometric property of a hyperbola. Okay. Yesterday we talked about ellipses and how any point on an ellipse, when you take the distances to the foci, they add together to be the same thing. Well, now on a hyperbola, when we take our distances, they're going to subtract to be the same number. Okay. So let's go ahead and write down what a hyperbola is. So first of all, just like with all of our other conics, we're going to have hyperbolas that open horizontally like this one, or we could have hyperbolas that open vertically. Okay? Every hyperbola will have a center. Every hyperbola will have two vertices and two foci. And something different about the hyperbola compared to our other ones is that we have asymptotes that cross through the center. Okay. So I'll have you write down the geometric property that a hyperbola is the set of all points. The difference of whose distances from 2 points, the foci, is a positive constant. So here is our geometric property, what you just discovered with your measurement of the distances from coordinate to foci. The difference will always be the same. I also have a note down here about the transverse axis. I'm probably not going to call it that, but you'll see it referred to that in your book. But notice how this hyperbola up here, it opens in the horizontal direction. And from the center, both vertices and both foci are horizontal from the center. Okay, we have a horizontal hyperbola because the transverse axis, what goes through the foci, the center, and the vertices, is horizontal. Okay. So much like yesterday with our ellipses, the center, vertices, and foci will all lie either horizontally or vertically from each other, depending on which kind of hyperbola we have. Okay, so let's talk about the standard forms of a hyperbola. Okay, so first we're going to talk about the horizontal hyperbola. Our horizontal hyperbola, notice how this looks very similar to our ellipse equation. The only thing that is different is this subtraction sign right here. Well, I guess I shouldn't say the only thing, but that's the big thing. So ellipses had x squared and y squared, but we had addition in between. Here we have x squared and y squared. However, the x squared in this case is the positive, and then we're subtracting the y squared. Okay. Please pay attention to this note. A is always going to be with this first variable here. Okay? It doesn't matter if A is bigger than B, B is bigger than A could be the same as B, but A is always the one that's associated with a variable that has the positive in front of it. Okay, it's going to come first in our equation. Okay, A is still going to tell us where our vertices are, and C is still going to tell us where our foci are. However, this time we get to use C squared equals A squared plus B squared. our foci will always be further out than our vertices from the center. So like I said, A is still going to tell us where our vertices are. So notice how I have, I'll color it. Here is a center. And notice how I have labeled that these vertices are going to be A units away. So much like yesterday, we're going to plot our center. We're going to move out A for our vertices and then write them down. We are going to calculate C. And C away from our center will be our foci. We're going to talk through the vertical hyperbola before I tell you how B is going to affect all of this. Okay, but A is still going to give us how far away our vertices are. C is still going to give us how far away our foci are. But this time the foci are going to be further away because C squared is A squared plus B squared. Okay, so now if we're going to have a vertical hyperbola, okay, what do you think is going to be different about our formula? This time, the y minus k squared is going to be the one with a squared because it's going to be positive, and we're going to be subtracting the x minus h squared. And since we're subtracting the x minus h squared, then b squared is going to be in the denominator. Okay? Remember, A is always going to be associated with the positive squared variable. Okay? Our center is still at HK. Please pull the H first, then the K. This is going to be, you're going to have to think about this because the Y is coming first in our equation, but we still need to pull the X first and then the Y. Okay. Now, let's talk about the graph. So what's going to happen, like we've talked about, we're going to graph our center, and we're going to graph our vertices A away. Since our hyperbola opens vertically, then our vertices are going to be vertical from the center. Now, what are we going to do with B? B is going to help us with our asymptotes. Okay, so we are still going to very, very lightly, it's kind of like an imaginary dot. We would plot B kind of like we would if we had an ellipse, but they're not coordinates, they're just reference points for us. And then very, very lightly, what I'm going to have you do is create a rectangle that goes through the vertices and then those B coordinates that you just plotted. And what is going to happen is your asymptotes will go through the center and through the corners of this rectangle that you lightly drew. And that is how we are going to get our asymptotes. So we're going to plot our center. We're going to plot our vertex points. We're going to go in the other direction, B, so that we can create this rectangle. Let me get my highlighter. We're going to create this rectangle that goes through those 4 points, and then our asymptote will go through the corner. Okay. Now, I want to remind you of how to write a line in point slope form. If we know a coordinate and we have slope, then the equation of our line is y minus y1 equals slope times x minus x1. What is nice about these asymptotes is that both of the asymptotes go through the center, and their slopes are going to be opposite of each other. So if you have a slope of 2, your other one has a slope of -2. If one has a slope of 5 halves, the other slope is -5 halves. So we're going to be able to tell our slope from our picture using A and B. And then the point that I want you to use for point slope form is just going to be the center, because both lines go through the center. And I'll ask that you just leave it in that way. Okay. Okay. So my goal is to do 2 examples here. So let's go ahead and do that. Hopefully things become more clear as we go through these examples. Go ahead and write this one down. We have x squared over 9 minus y squared over 25 equals 1. And I want you to turn to your neighbor and tell them which direction you think this opens. This is a hyperbola that opens horizontal. We know that because the x squared is the positive squared variable. Okay? The x squared is the one that's positive. Okay? Also, let's take a note that a is 3 because a squared is always with the positive variable, and b would be 5 because b squared is always the denominator of whatever's being subtracted. Okay? Okay. Now, there is nothing being added or subtracted inside of the squared variables, which means our center is at 0, 0. Okay, go ahead and plot that. Okay, well, we know that a is 3, and we just determined we have a horizontal hyperbola, so I'm going to move 3 horizontally from our center and write down that our vertices are at 3, 0 and -3, 0. Let's also keep in mind that c squared is a squared plus b squared. Our a squared is 9 and our b squared is 25. So our c squared is 34, which means c is radical 34. Okay? Well, radical 34 is not quite 6. Radical 36 would be 6. So radical 34 would be almost 6. So from our center, I'm moving out radical 34. Okay, so our foci end up being 0 plus radical 34 and 0 minus radical 34, comma 0. Okay. If you have an irrational value, you can combine and write the foci as one coordinate even though it's 2. Okay, that doesn't bother me. Okay, so let's go ahead and figure out where our asymptotes are so we can actually draw this curve. Okay, so in green, because it's going to be very light, I'm going to take note that since b was 5 and b was associated with y, I'm going to move vertically 5, 1, 2, 3, 4, from the center. And these aren't actually coordinates, okay? And remember, if I'm doing something in my green pen, it means I'm doing it very, very lightly, because in this case, it doesn't even exist, okay? But I'm going to connect these with a rectangle, okay? And what this means we want our asymptote to go through the center and the diagonals, or the corners, okay? So center, corners, these asymptotes go through. Okay? Now, let's go ahead and finish off this hyperbola, We know that from our vertices, our hyperbola needs to approach our asymptotes. So I'm going to go ahead and draw that in. And we need to actually write down the equation of these asymptotes. Now remember, both of these asymptotes go through the center. So I'm going to use our center as the y1 and the x1. So our center is 0, 0. So I have y minus 0 equals our slope times x minus 0. I'll write that for you so you can see. And then our slope, we can use this picture. Okay. If we look at our center right here and we count up and then over, if I count up and then over, we are going to go up 5 and over 3. So our slope is 5/3. If I look at the other one, we would go up 5 and left 3. So that slope is negative 5/3. So I'm just going to write it together. Y equals plus or minus 5/3 x would be the line, or the two lines that are our asymptotes. If you're needing some clarification from a neighbor, use this time now. What's nice about hyperbolas is we're kind of in the routine of graphing ellipses where we use A and B in the particular directions. We're still using A and B, we're just using them in a different form to get a different shape, but we're still moving out A and out B in the direction that it's associated with, whichever variable it's associated with. Okay, we just need to make sure that we're careful of if it's horizontal versus vertical, depending on the which one is positive, which one is being subtracted. Okay, let's go ahead and look at one that is not in standard form. We know that this is a hyperbola because we have two squared variables, x squared and y squared. However, one's positive and one is negative. Okay, so we know that it's a hyperbola because of those two things put together. Let's go ahead and get this into standard form. So, since we have a coefficient of 16 with our y squared, let's factor that out, which means we would have to factor it out of 64y as well. And we'll leave room to complete the square. Our x squared has a coefficient of -1, so we'll factor that out of the x squared term and the x term. So notice how this is going to become minus 2x. We'll leave room for completing the square. And then I'm going to move the negative, or the 47, I'm going to subtract it over because we know we're going to want all of our constants on the right side, just like we did yesterday. So now, to complete the square, b over 2 squared would give us 4. But remember, this 4 is being multiplied to that 16. So this is really 64 that we're adding. Be very careful here. To complete the square, this would be 1. But 1 is being multiplied by that negative outside of the parentheses. So to balance our equation, we would need a negative 1 over here. So when we actually, when we rewrite this, this is going to be 16 times y plus 2, the quantity squared, minus x minus 1, the quantity squared, equals negative 47 plus 64 plus negative 1 would give us 16. Just like with an ellipse, we need this to equal 1. And so I'm going to divide both sides by 16. So here is our standard form equation that we need to be working with. Let's make a couple notes. Let's make a note that this is going to be a vertical hyperbola because the y squared is the one that is positive and we're subtracting the x squared. Also remember that a squared is always associated with that positive squared variable. So in this case, a squared is 1 and b squared is 16. Okay? A squared, no matter if it's bigger or smaller or the same, a squared always comes with that positive squared variable. Okay? So let's identify the items that we need. Our center, please be careful here. Please be careful here. Remember, we need to grab the x, then the y. It's very tempting to write our center as the order in which we see it, but our center really is 1, negative 2. Okay. Since a is 1 and we have a vertical hyperbola, I'm going to move 1 away from our center in the vertical direction to get our vertices, which would be 1, negative 1, and 1, negative 3. C squared is a squared plus b squared. So in this case, c is going to equal radical 17. We know that radical 16 would equal 4, so radical 17 is just a hair more than 4. So from our center, I'm going to move 1, 2, 3, 4, a little bit more. 1, 2, 3, 4, a little bit more. Radical 17 away from the center. And we did so in the vertical direction. So our foci would be 1, comma, negative 2 plus or minus radical 17. Because vertically, which is affecting the negative 2 part of our coordinate, the y coordinate, we moved radical 17 in each direction from the center. All right, to make our asymptotes, we need to take b into account. So since b is associated with our horizontal variable, I am going to move 4 horizontally. And very lightly, because it doesn't even exist, I'm going to make this rectangle connecting the vertices and these b coordinates that I just made, so that we can create an asymptote, 2 asymptotes, going through the center and the corners, making diagonals. So our vertical hyperbola is going to look like this. We're going to approach those asymptotes. And our last job would be to identify the equations of those asymptotes. Okay. I'll write it down again. Y minus y1 equals slope times x minus x1. Remember, our center is a part of both asymptotes. So to save us time, we are going to use the center as the coordinate that goes through our lines, or our asymptotes, with our lines. Okay, so 1, -2 is our coordinate. Now, if we use this to count our slope, okay, if we use this to count our slope, then from the center, we would go up 1 and over 4. So our slope would be plus or minus 1/4. One of them has a positive slope, one of them has a negative slope, but see how the A and B are going to give us our slope. Now, depending on which direction your hyperbola opens will depend on whether you have A over B or B over A slope. If you want to recognize that and associate them together, that is fine. But I think it is best to think about what your picture looks like and count the slope with the graph that you have already drawn. Okay? I think that we're all pretty good at counting slope. So once you have your picture drawn, just count the slope on your graph. Okay? So for each hyperbola, make sure we're getting the center. Use A to find your vertices. A squared plus B squared equals C squared. Your foci are going to be in the same direction from the center that your vertices were. They're just going to be further out this time. And then B will help you draw your rectangle so that you can identify your asymptotes. Okay. Any remaining time left in class should be spent beginning your assignment. I think it would be a good idea to work together as a pod on maybe the first couple of problems to make sure that you have an understanding of what is going on. Please make sure you do your homework and you check your answers with my key that I have posted online. Tomorrow we will go over questions and then have a short quiz.